Okay, thank you very much, Professor Bagherifard, for the introduction. And let me reintroduce myself. My name is Romario. I'm a PhD student in Politecnico di Milano, and today I'm going to present the influence of powder morphology on both, I'm sorry, bonding mechanism in cold spray additive manufacturing of copper alumina composite. So as my colleague has already described how these cold spray works, but in my specific research here, we also incorporating not just the metal, but also the ceramic particle. Since the cold spray work with the high velocity impact, so ceramic will tend to fracture during the high velocity impact. So, and that's why the metal particle here will play the crucial role to achieve the good bonding, acting as a binder and promoting the mechanical interlocking for the ceramic and also metallurgical bonding for each metal. And on the other side, the ceramic particle will contribute to improve the performance of the deposit. Okay, in this study, we compare the different metal morphology, which is the dense, smooth spherical copper. On the other side, we have porous and ligament structure spongy copper. Uh, both these copper will be mixed with alumina, angular alumina, as you can see in this slide. So here, and this is the microstructure of the powder, of the initial powder. We can see this spherical has more uniform grain. And both system will be sprayed with identical spray condition with the gas temperatures 425 degrees Celsius and gas pressure 30 bars with nitrogen as the working gas and 20 millimeters per second travel speed and 20 millimeters stand of distance. Based on this parameter, we use this parameter for this kinetic spray solution, and we get the flight dynamic of the particle. And what we get at the end is the impact velocity and temperature the particle. This is important for us because if we want to understand the interaction, we are limited to the real-time observation since this process, this deposition will occur at a very fast scale and very small scale, and that's why we create the numerical simulation implementing the cohesive, the hybrid couple Eulerian Lagrangian with cohesive zone model, especially for the ceramic. And to we also apply the Rosen-Rummel equation to make this particle size distribution reflect the actual particle size distribution of the powder that we have. Based on these parameters, then we run the simulation. As you can see, we can extract, with this simulation, we can extract temperature, stress, and also we can also extract these strain as the thermomechanical response during the process of the deposit. In this slide, you can see here, the red pink blocks here is the ceramic. It's represent the ceramic. So at the interface of the ceramic, we can see here, we have a peak in strain and temperature due to the flowing of the metal during the process, as the ceramic here act as the rigid inclusion, so the metal will flow. And because of these deformation in very fast time, so we increased the strain and temperature during the process. And compare these spherical and spongy, we can see these from each peak, we can see this smooth line. Compare here, it's more jagged. So here we can say that this happened at the interface of the particle. Meanwhile here, it can penetrate it into the particle core. Okay, it's not clear to see what happened during the process, and then we decide to run the experimental study. So we start from 100% copper to 100% alumina, which we got here. It's totally erode the substrate. With the deposition efficiency, it's 0. And with increasing of the alumina, we increase the ceramic retention in the deposit. And also at certain point, we reach the plateau here at around 40% of volume alumina in the feedstock. After that, we have decrease in deposition efficiency value. After that, we focus on the small addition of ceramic. Just we want to see if this small percentage of ceramic can, how can I say it, can affect on the deposit. So as you can see here in the pure copper, we can see these internal core is still there. So we have this EBSD image, and however in the spongy we have more thicker grain refinement at the interface, which validate our simulation. We have higher and more distributed strain accumulation inside the particle. Meanwhile, in addition of the alumina in the deposit, we intensify the process. As you can see here, the grain is thicker, the interface is thicker, the grain refinement is thicker, and even here in the spongy, we have we can say that this is the strain accumulation inside the core of the particle. And these grain boundaries image further validate this finding that we have this bridge between these first bridge to here, which we still have this in 60-degree anneal twin angle that we have here in these powders still remain in here in the spherical. However, in spongy, we remove this fingerprint of the particle. And we also did the nano indentation result to see further performance of the deposit. As you can see here in spherical copper, even with the addition of ceramic, the range of the average hardness is still there. It's around 1.4 to 2.2 gigapascal. However, in the spongy, even with pure spongy, we achieve higher nano hardness compared to the spherical one. It starts from 1.8 to 2.6 gigapascal, and in addition of the alumina, it's globally shift the hardness from 1.8 to 2.2 until 3 gigapascal in range. To further validate these results, then we run the XC2 test in a nano compression sample, and we can see here it's two completely different response from the spherical and the spongy. From the spherical, it's around 248 gigapascal. However, in pure spongy, we have 422.13 gigapascal, which is around 60 to 70% increase just by change the morphology of the particle. However, by adding the ceramic here, we also increase this, we improve the performance as we introduced in the earlier slide that the addition of ceramic will improve this performance of the deposit. And at the end here, we want to see in clear detail what happened during the process. And what we observe here, this is the in situ microcompression test result. So you can see here in spherical copper, the trajectory of the crack is directed to the location where we have the ceramic. However, in a spongy sample, at some point we can see here, even with the closest alumina here, it's try to avoiding these, and it's showed that in spongy we have more mechanical interlocking. So we have more in mechanical interlocking in this sample. So at the end of this slide, I would like to conclude my presentation. So it's also important to consider the morphology of the powder alongside with the process parameters and the material selection, because this morphology of the powder will determine how the particle deform, the mechanism between deformation of the particle. This deformation of the particle will dictate how the microstructure, final microstructure of the deposit. At the end, it will dictate how the material perform under loading. That's all my presentation. Thank you very much.